Last time we have discussed how to write the circuit equations for an LR circuit. Now, in this video, we are going to solve these equations. So the problem in here is expressed like this. So there's a switch in here. The switch has been open for a long time. Then at time t equals 0, it is closed. And after that, of course, there is a current start flowing. So we would like to find the current at a later time t. So as a result, there's a current which is a function of time, and we would like to find this. That's basically the problem is asking us to provide that function. Now, there's an initial condition in here at time t equals 0. There is something stated, some physical thing has happened. This actually implies something about the initial values of some quantities. So we are going to say that this implies that the value of the current at time t equals 0 should be taken as 0. And I'm going to explain why this must be the case. So that's the problem. Since there are no directions chosen already chosen on the circuit, so I have to choose my own direction. So let me choose the direction of the current like that. And let's just remember how we write down the circuit equations. We just think of it as this thing as equivalent to a circuit where there's the inductor is replaced by an EMF device. The other devices are there. The switch has been closed, so the EMF is in there, the resistor is there, and the inductor is replaced by an EMF device with an EMF which is equal to minus L di over dt. As a result, I'm also going along that direction. If you just write down the loop rule, the sum of the EMFs is equal to E plus EL, and the sum of the potential drops is equal to IR. So therefore, this is our equation. So finally, we just express the EMF on the inductor by the Faraday's law expression minus L di over dt. So that's our equation. This is the equation that we would like to solve. And then the initial condition problem. So in all differential equations, of course, it turns out that the equations have many solutions, infinitely many solutions actually. There's some kind of a free parameter in there. We can only determine that free parameter by applying some condition. And that's actually, most of the time, it's an initial condition. So at time t equals 0, when everything starts, there's something happening expressed in physical terms. That's basically the closing of that switch in here. But this has a mathematical meaning. So I said that this meaning is that the current at time t equals 0 is equal to 0. Let's try to see why. So I don't have much space in here, but let me just do it in here. So let's suppose we draw the current versus time graph. Current versus time graph, right? So we know that I'm going to use a thick yellow color for drawing the curve so that we can distinguish it. So we know that before time equals 0, the current is definitely 0. At time t equals 0, the switch is closed. So suppose that current suddenly jumps. So there's a jump discontinuity. So therefore, the initial value of the current is non-zero. So I don't know what happens next. We are going to find out. But let's suppose that there is a jump discontinuity in here. Right, so let me write Z in here. So jump discontinuity. At t equals 0. So if that's the case, in that case, this essentially implies that the time derivative of the current at t equals 0 is infinite. It is plus infinite, but it doesn't matter what it is actually. So the current suddenly changing is essentially means that it is infinite. So you can think of it like this. I mean, of course, discontinuities are just mathematical constructs. In physics, of course, we never have discontinuity. So wherever there is a discontinuity, of course, there is actually a very sharp change over a very short amount of time. Who knows how short that time is? But in any case, there is a very steep slope in here where the current increases. So you can use this kind of a thinking to actually realize that the time derivative of the current is infinite in there. So what does that mean? There's this physical condition in here now. So the EMF on the inductor is the time derivative of the current. So therefore, that means this implies that the time derivative of the current, the EMF is also equal to infinite. That's actually minus infinite, but that's also irrelevant. In that case, this equation cannot be satisfied. That essentially implies some kind of an infinite back EMF produced on the inductor. And this is something that doesn't happen. So there's always a back EMF. So an EMF is produced over there, but it is never infinite. So as a result, a sudden change in the current can never happen, because whenever current wants to change suddenly, let's say, the back EMF basically dumps it down. So as a result, it just produces some kind of a back EMF in the air. So it just slows it down. So therefore, the current becomes continuous again, right? So as a result, this is what we say. This never happens, right? This is not possible. That's not possible as well. So what is possible? Let me redraw the same thing. Unfortunately, I can only do it like this. Let me redraw for completeness and with a thick line. So it can only happen something like that. So as a result, the current has to be continuous. The current has to be continuous, but its derivative may change discontinuously. So the slope before that time was equal to 0. But slope after time equals 0 might be non-zero as well. So there's no problem with this. There is no problem with the slope in here. But the current versus time graph is continuous. The current cannot change discontinuously if there is an inductor in the circuit. So that's one of the functions of the inductor. Actually, it prevents sudden changes or fast changes of the current. Of course, we are going to see this feature in a moment too. So just keep in mind that we don't have to place an explicit inductor inside a circuit, because we know that any kind of a circuit has an inductance. So if you just form a loop of circuit like that actually has an inductance, but this inductance value is very small. But doesn't matter how small it is, as long as there is an inductance in there. This prevents sudden changes in there. So there might be some quick changes of current, but it never displays a discontinuous jump. So there's always a continuity in there. So that's one of the arguments. So therefore, let's just go back to the beginning of everything. So the statement that the switch is closed at time t equals 0 actually tells us that the current immediately after the switch is closed is the same as the current immediately before the switch is closed. So you can think of it like this. The current at time t equals 0 plus. Please understand this as immediately after the switch is closed. And the current is equal, current immediately before the switch is closed. So that's the continuity statement. But since before the switch is closed, the current is equal to 0, then from here we just get this information that after the switch is closed, the initial value of the current is still 0. Right? That's the information. So that's the first thing. So as a result, we have to solve this equation. Let me write it down like this. Solve with initial condition that the current at time t equals 0 is equal to 0. So that's our equation to solve. So that's our job in here. Let's go ahead and see how we can solve it. So I'm just going to move these terms around a lot. So let me start with the same equation. So E minus L di over dt, that's equal to R times I. That's a differential equation because it involves the derivative of a function. So it's an equation for a function. So usually what we do is we just express the derivatives. This is basically for first order differential equations. So we just express it in terms of the rest. So that's the first step that we can take, plus E over L. Let me check and see if that's correct. All right, so the time derivative of I is equal to something multiplied with that function plus a something. So if you remember, the last time that we have tried to solve this kind of an equation in RC circuits, we said that this additional constant bothers us, but we can get rid of it. So that was the idea in here. In any case, you are going to learn the techniques of solving these kind of equations later. I'm just going to give you some ideas in here. So as a result, you don't have to know any of these. But I mean, usually these kind of equations have a similar kind of solution. So what we do is we just, I express this as this constant multiplied I plus a constant, which is I minus E divided by R. All right. So the time derivative of I is equal to this. Now I just call this expression as my function. I just give any arbitrary name to it, so I just called it as y. The nice thing is that the left hand side is also equal to the time derivative of y, because y is equal to that function plus a constant, but the constant has zero derivative, so therefore the left hand side is 2. So as a result, this equation is like that. Time derivative of y is equal to a constant times y. So that's a trick to eliminate this additional constant. But the cost is that, of course, I'm now using a different function. But in any case, that's not a big deal in here. Next, we have said that, I mean, this is basically by experience. If the function is like exponential of a constant times t, time derivative of y would be constant times e to the constant times t. So that's this kind of a function satisfies the property that the time derivative of y is equal to that constant times y. So as a result, this is this kind of an equation. So we just use this idea in here. So since we know the exponential function very well, we just write down the y function like this, e to the minus r over L times t. So that's the constant in here. And then finally, we say that, well, there's a, if I multiply this function with another arbitrary constant, it's not going to change anything. So the equation is going to be the same again. So if y satisfies this equation, then a times y also satisfies. So there's always an arbitrary constant of proportionality in here. So we need to determine that constant with initial conditions, basically. So as a result, I don't know the value of this thing, but I know that it is there. Finally, the current is, therefore, is equal to a times e to the minus r over L times t plus e over r. So I just combine the definition of y. I re-express y in terms of I, and then we get this. So that's the solution. I still didn't use the initial conditions, so I insert at time t equals 0. I know that the current would be 0, but this equation gives me a times exponential of 0 plus e over r. Exponential of 0 is equal to 1, so therefore this means that my constant a should be minus e over r. So I just combine these two, and as a result we get the current as E over R times 1 minus e to the minus RT over L. That's our expression. And then after that we just do some simplifications, and we just try to understand this equation and see that, well, probably we could have guessed this and we could have guessed that and things like that. So let's start with this. First of all, the argument of the exponential is always dimensionless. So e to the something, if there is something in here, x must be dimensionless. So that means RT over L is also dimensionless. That means L over R has the dimension of time, right? Has dimension of time. So we just call this as the time constant, L over R. The inductance divided by the resistance is the time constant. It's the time constant of LR circuit. From here we also see that the Henry divided by Ohm should be equal to the seconds. So that's why I was able to say that Henry is 1 Henry is 1 ohm second. So somehow these units also should satisfy that property, right? So as a result, I can write down the current as E over R 1 minus e to the minus t divided by the time constant. So the argument of the exponential is the ratio of 2 times, so therefore it's dimensionless. The rest is basically EMF divided by R is the current. We know that it has the dimensions of current, so therefore on our side we could not have any other expression in there. Okay, so next thing, of course, we just plot this. Let me do this. So the current is EMF divided by R, 1 minus e to the minus t over tau. So time in there, the current is in there. So there is a very special value of E over R in there and time 0 in there. So let me plot this with the yellow thing again, with a thick yellow line. So before time t equals 0, my hand shook, all right. Before t equals 0, the current was equal to 0. After t equals 0, the current starts from 0, but it rises. When time goes to infinity, you can see that the exponential goes to 0. So as a result, this goes to this behavior. So it has this exponential decay of that constant value to that constant value in here. So that's E over R. So we also have the same thing about the time constant. Let me state it like this. So in one time constant, of course, we have exponential is like the argument of the exponential would be minus 1. So therefore, this is 1 over e. So it was 1 over 2.7. We have said that this is about 63% or 0.63. I'm sorry, 37%. 63 is the other one. So that means during that time, the current level rises from 0 to 63% of its final value. 63% of E over R. You can think of it like that. And we have discussed this before, so there's still a 37% of rise that's left in here. There's a 37% of rise left. So whatever it is left, so 63% of that is that increase takes place in the next time constant. So from tau to 2 tau, there is this additional raise again, and so on. So as a result, you see that after a few time constants, after 5 time constants, you can practically say that you have almost reached to that maximum value, because this exponential is decreasing very rapidly. So in 5 time constants, you can kind of assume that this exponential factor is negligible. So in reality, of course, mathematically at least, the current never reaches to that value, but there's a point where, for all practical purposes, we say that the current has reached to that final value. Okay, so less than, that's the function of the time constant. So it's the same discussion again as in the discussion for the our RC circuits. So it has the same job in here. So let me erase everything in here about the time constant and things like that. So let's just forget about this. What happens is this. Let me also erase this. So you can see that the current was 0 before the switch is closed. And if you ignore this time over which the current changes, and changes significantly, after a certain time, the current has reached the value E over R. So as a result, that's one of the things that we can say. So let's say it like this: as time goes to infinity, right, current reaches to a final value. Its final value E over R. Of course, in all of these decaying I'm going to draw the picture again. So this was our circuit. The EMF is there, the resistor and the inductor in here. So after a certain time, of course, the current everything reaches to a maximum value. I'm sorry, it's not the maximum, but a final value, unless there's some kind of an oscillation that stays there. So in these kind of LR circuits, of course, after a long time passes, that means much larger, after a time larger than much larger than the time constant of the circuit. In that case, you will see that all relevant quantities on the circuit has reached to that final value. So I don't know, that might be the potential drop on the resistor or the current on some branch and things like that. So it will reach to a certain value. So let me say it like this: after some time, we are going to have the current is almost a constant, which means the rate of change of the current is going to be almost 0, which means that the EMF on the inductor is going to be almost equal to 0. So as a result, the current reaches to a final value. It doesn't change anymore. So in that case, no EMF is produced on the inductor. So from that perspective, the inductor has no function anymore in the circuit. So as a result, you can just simply replace this thing with a wire, right? So because somehow it doesn't contribute anything to the circuit. So the inductor makes its presence known only if the current is changing, in which case it produces an EMF. But if the current is not changing anymore, then it is as if it's not there. So just replace it with a wire. Of course, there should be a connection in here because somehow we know that there's a current flowing. So therefore, I just replace the inductor with a wire. So, and of course, if you look at this circuit in that case, if you just forget about the inductors, it's just a resistor connected to an EMF device. So it's a known DC circuit. So as a result, it is quite reasonable that the current has reached the value of E divided by R. Right? At infinity, of course, we get this value. So as a result in here, therefore, we could have guessed that the current would settle to that value, which is E over R. We could have guessed this easily, so that's something that would definitely happen a long time after. Also, we could have guessed that, of course, before switch is closed, the current is zero. So essentially, what happens is that when I close the switch, the current changes from this zero value to that final value, but somehow the presence of the inductor prevents this sudden change of the current, so therefore the current changes slowly. Right? Let's think of it like this, or let me just start with a thing. So let us suppose that we have a circuit with a resistor and there's also a switch in here, EMF and the resistor, and let's suppose that there is nothing in here, just wire. So we close the switch at time t equals 0, and this is what we observe for the current. I'll do it like that. So it is constant before, and it is constant after the switch is closed, because immediately after I close the switch, the current suddenly jumps. So there's also a time scale of jump in here, but that's very short. In any case, we can also talk about this time scale too after we settle this thing. So now I change the circuit a bit. So instead of a wire in here, I just place a small inductor in here. Let's say it like this. I'm going to place a small inductor. So in that case, in the current versus time graph, this part of the graph doesn't change. The limiting value of that part is not going to change. It's only this intermediate part which has changed. So let me draw this part now. So as a result, this is going to the current is going to increase like that. Let me also show the value of E over R in there. Okay, what is that? There's of course a typical time in here where the current rises. So this is typical time. You can take it when current rises, current changes. So current now changes continuously. There's no discontinuous change. That was the function of the inductor basically. But what is the time scale in here? It's just a few time constants. But let's just say that this is equal to a time constant. I have said that in 5 time constants, you can say that practically the current has reached to its final value. But let's say that this is a time constant. So therefore, this time constant is equal to the inductance value divided by the resistance. All right, but the inductance is small in here. What happens if I replace this with a big inductance, an inductor with a big inductance? In that case, the time constant will rise, and so therefore, I'm going to have a graph where the current now rises much more slowly over a larger time scale. So I'm going to do it like that in that case. So this is then the typical time when the current changes. So let me also erase the other times in here. So that time has no relevance now. So the time scale where the current changes from the zero value to its final value, this time is larger because I have placed a larger inductor in there. Okay, so let's then come back to the initial thing that we have started with. So that's an erasure. So I said that just replace this with a wire. There's just a wire in here. Of course, there's no inductor in there, but I have said that every circuit has an inductance. But this is very small. Let me say extremely small in here. We haven't come up with any value of the inductance, but only for one example we have computed mutual inductance for 2 circuits which are 1 kilometer away. the value was around like 10 to the minus 15 Henry. In any case, I don't know the typical values of this inductance for a circuit without an inductor, of course. But there's an inductance, so whatever it is, therefore, I can still say the same thing. So I said that there is a discontinuity. No, there isn't. There's actually a very fast change in there. So there is a time constant in there, but this time constant is so small that we don't notice it. So probably it's much smaller than a second, perhaps smaller than 1 over 10 seconds. So in that case, of course, we don't notice anything. We cannot notice anything shorter than 0.1 seconds, basically. But this is something that can be measured with some appropriate devices as well. So in that case, the typical time when the current changes is very short. So as a result, we think that there is a discontinuity, but there isn't actually. And this can actually be computed with some difficulty perhaps. That time scale can be computed if you just get an estimate for the value of the inductance of the circuit. Okay. So therefore, that's basically the function of the inductor in a circuit. It just prevents sudden changes of the current. It doesn't prevent the changes of current. It just makes the change to be a little bit slower. And better the inductance, that means larger the inductance, slower the change. When the inductance increases, you see that the change of the current takes place over a bigger time. That means it will change much more slowly.